Organic molecules are quite flexible. They can bend, rotate, spin, collide, vibrate, and change shape, even though most of these events are not visible to you. One such unseen act that is significant to organic chemistry is the rotation of atoms around the single bonds. This causes the molecules to adopt various spatial arrangements or shapes and easily interconvert between shapes by bond rotations. The atoms holding the other bond types, that is the double and triple bonds, are rigid. If one tries to rotate such a bond, it will break, so they don't entertain such prohibited practices of bond rotation. And for that reason, it is an absolute privilege of the single bonds to show conformations, and a specific conformation is called conformer or conformational isomer. Let us look at our own body as an example. Standing and sitting are two positions we can adopt, which are easily reversed just by rotating our hip and knee joints. So the shape taken is erect and bent. Like that, there are plenty of such comfortable and uncomfortable shapes our body takes and gets out of due to the rotation of our joints. Single bond containing molecules do the same. For instance, it is hard to see any significant change in shape if one rotates a simple CH bond of CH4 or an HH bond of the H2 molecule. But in larger molecules like in 2-carbon ethane, keeping one carbon end fixed and rotating along the CC bond leads to many possible arrangements. It will be hard to isolate pure conformers because the single bonds in the molecules will rapidly rotate and adopt infinite possible conformations at normal temperatures. If there is a substituent group on the second carbon, then interelectronic repulsions come into play, due to which some conformations will be preferred and stable over the other. In such cases, the most common conformations will be those where the groups are placed at a bond angle where there is least repulsive interactions. The potential energy of the molecule will be minimum, which would also hint at its higher stability. In such molecules, the energy required to undergo any sort of bond rotations, called the rotational energy, is higher. This implies a higher barrier for bond rotations, making it more difficult for the molecule to change its shape frequently. Conformations can be seen in open chain and closed chain carbon compounds. Conformations are drawn using Newman and Sawhorst projections. Some of the common terminologies encountered while talking about conformations are eclipse, staggered, skew, anti, planar, boat, and chair conformations. Conformational isomers are covered extensively under the branch of stereochemistry that considers molecular shapes and studies the reactions. So next time you see a molecule existing in different arrangements that bond rotations can easily interconvert, be sure to remember conformational isomers. They are bent but surely not broken. Subscribe to Curly Arrows for more such content. For organic chemistry tutorials, become a premium subscriber today.